Today we are going to be talking about the very important concept in machine learning, and that is bias variance trade-off. So it's actually called bias variance trade-off of squared error. So in short, we call it bias variance trade-off. Before now, we've gone through the lesson on overfitting and underfitting. We also try to relate it to model flexibility as well as model complexity. So if you have problems understanding this, we are going to review it now for sure, but I'll also recommend you go back to this lesson, as you can see here, this underfitting and overfitting, where we discuss bias variance trade-off in part. So today we're actually going to be looking at the bias variance trade-off formula, or the bias variance trade-off equation, and see what different terms of this equation actually mean. And in machine learning, sometimes you actually need to memorize some things. So this is one of those lectures you need to memorize this formula and then get it into your head. Maybe by writing it a number of times, you get used to it. So let's get started. Again, this is a procedure-based class, so everything is written clearly. In case you miss out anything, you have it there on my website, and you can find the link to this page on the description box below. All the lessons in this course, Machine Learning 101, the pages are always there for you to follow along. All right, so let's just remind ourselves about when we talked about linear regression or regression generally. So we have a training data set made up of X and Y values. So these X and Y values have X1, X2, X3, X4, and have Y1, Y2, Y3, Y4. So what happens here is that we now are given X0 and we are told to find Y0. So that is what the starting point of all of this. Remember to subscribe to my channel. In case you've not subscribed, just click on the subscribe button below. In case you motivate me to continue making these lessons, and also you get notified when I make an update. All right, so but before we can estimate y, we need to try to figure out a relationship between x and y, and that function, or we represent this function as a function of x is equal to y. So using this function, we can find x0 to be f of x0 equal to y0. So we put this little hat to show that this is actually what we estimate. Now, this estimate we are making based on this function we use may not be exactly the same as the real value. So what we are saying is that y0 that we calculated may just be approximately y, so it's not exactly equal to y. So bias variance trade-off focuses on the difference between the actual value and the value we estimated. So let's go down a bit. And this difference is represented as MSE. MSE, right? Good. So this is called mean squared error. So this mean squared error is simply this minus this squared and sum it over all the values that you estimated. So in this case, we have x1 bar, y1 bar, y2 bar, y3 bar. So you sum up all the differences, all the errors, and you take the square of it. And that is called the mean squared error. So the formula, I can write error in y0, the actual value minus the value y0 minus f of x0. That is the value you estimated, right? So this actually is squared. Okay, so now this can be decomposed into three terms, and these three terms are, one of them is variance of whatever you calculated. Then we have, now you need to know these terms. You need to know the second one is squared bias of whatever you calculated. And finally, we have variance of the error term. So these are the three items that this MSE mean square error can be broken down into these three terms. So writing it out completely, I'm writing it out so that I'm trying to help you understand that you should actually know how to write out this equation. So y0 minus f of x 0. In my website, the f doesn't have a hat, but you should actually put a hat in it. So the first one is the variance of f of x0 plus the squared bias, the bias of f of x0, and now we are talking about the squared bias, plus the variance in the error term. So we have an error term. And you remember the focus of model fitting or regression is to minimize this mean squared error. So what can we do? We can minimize the variance. We can also minimize or reduce the squared bias. Now we cannot reduce the error term or the variance of the error term because this is error that we cannot actually determine the quantity or even the source. So now if you are reducing the variance, the bias will actually be increasing, and if you are reducing the bias, the variance will also be increasing. So now if you decide to reduce this term, this EMS, this mean squared error MSE, and you decide to start reducing the variance close to 0, at a point the bias will also increase and it ends up cancelling out whatever you've gotten. So let's examine what the graph says. Besides, I have a beautiful explanation of the meaning of the bias as well as the meaning of the variance, and so you can read it up. But now I want to examine what happens when you are reducing the bias, what effect it has on the variance, and what happens when you are reducing the variance, what effect it has on the bias. Now I'm going to use different colors now. So for the total error, total error we have black. The bias we have the bias squared, we have red, and the variance we have blue. So let's examine this curve to see exactly what is happening here. So we have in this case, this is the total error. The red curve, if it starts coming down, we are reducing the bias squared, and the total error is reducing. As you can see, the black curve is also reducing. At some point, the black curve starts going back up. So at some point, the total error starts going back up. Even though you continue to reduce the bias, the squared bias, the total error will increase. The reason the total error is increasing is because at some point, we also look at the variance. When you start increasing the variance, at some point the total error starts increasing. Okay, so this middle point where we have the lowest total error, this middle point you have the lowest total error, is called the trade-off point. So this is called the trade-off point, and that is trade-off between bias and variance, or trade-off between model complexity and model simplicity. So each time we always want to get at this point. At what point do we stop reducing the bias? Or at what point do we stop increasing the variance? So the black line represents the total error, the blue line represents the variance, and the red line represents the squared bias. So I'm not going to continue reading this. I'm going to actually refer you to this underfitting and overfitting because it helps give a few more details on this. So I'm going to actually stop here, and hopefully you've understood the meaning of bias variance trade-off. I recommend you take some time to do the Python practical because we actually plotted this in Python and see how we actually increase the model complexity and see the effect it has on the total error and how it relates to both underfitting and overfitting. So I'd like to thank you very much for joining Machine Learning 101. In Machine Learning 101, I can remind you that we are talking about only supervised learning. In 102, we are going to be talking about unsupervised learning. So we actually in 101 going to be moving between classification and regression because those are the only two topics in Machine Learning 101. So I'd like to thank you for viewing. Remember to subscribe and we'll see you in the next lesson.